Good morning. It looks like we have one more class, one more lecture on chapter 23. We have been looking at electric potential and electric potential energy. And we're ready to wrap it up today. This is our third and last presentation on this. So I went back a few slides here. We're into the topic of equipotential surfaces. And the idea here is that anywhere that we have a region of electric field, we can draw in what are called equipotential surfaces. Or vice versa. Anytime someone gives us a set of equipotential surfaces, we can draw in the E fields. So the rules here are the equipotential surface. Now, there are green lines here representing the equipotential surfaces. They look like lines, but that's because it's a side view, and they're actually surfaces. There's a couple of plates here. Those plates extend. Again, it's a side view, positively and negatively charged. That's a common geometry that we've been using and will continue to use to create a more or less uniform electric field, especially if we stay away from the edges, right? That's always good advice. Parents are always telling their kids, stay away from the edges. So, in one way or another. So if we stay away from the edges, the electric field will be pretty uniform, and that says we'll have nice parallel electric field lines drawn here in red. And then they will be crossing these equipotential surfaces that are evenly spaced. If it's a uniform electric field, those equipotential surfaces, they've labeled them here, 20, 15, 10, 5, 0, and that's what the pattern will look like. Now there's a lab which you may already be doing, there's a lab with this, and so you'll get a chance to go in and draw these. So stop and think about how these are related. What it comes down to is that there are going to be situations, I'm going to go through this example because we've already done this. There are going to be situations where going in and doing the exact mathematics could be complicated. It could take you all day to sit down and go through the mathematics of this, but a lot of times what you can do is if you know the charge distribution, you could do a quick sketch, and once you're familiar with the rules, you can draw in the E field lines and the equipotential surfaces pretty quickly. So this example is a dipole. Again, it's an equipotential surface example. How this picture would come together is this. We've got the E field lines in red, we've got the equipotentials in green, and I don't have the best color distinction in my vision, so if I say they look kind of like the same color to me, not so different sometimes. Anyway, I've got a positive charge, I've got a negative charge. Now if it's a dipole, the amount of positive charge matches the amount of negative charge. And that says if I look at all the E field lines directed away from the positive charge, it matches the number of E field lines directed towards the surface of my negative charge. So what I can do is just, one E field line at a time, I can draw these red lines. Now, I know with no other charges in place, these E field lines are going to spread out. So that's what whoever did this diagram did. And then when you work your way around to the back of the charge, because remember, starting at the charge, the E field line should be uniformly spaced. So this person decided to use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? 10? 11? Looks like 11. 11 or 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 8. I think it's 11. Lines coming out from each of these charges. They're evenly spaced around the charge, and that means the one here on the back side, they're going to have to start curving around because eventually they're going to have to lead us over to the negative side. So you could draw those red lines, and then once you've got the red lines drawn, how do I draw the equipotentials? And the equipotentials are drawn in a fashion so that everywhere an electric field crosses one of my equipotential surfaces, it crosses it perpendicularly. So good practice at drawing those perpendicular angles. But that's the idea, is kind of qualitatively we can predict what an E-field, set of E-field lines and equipotentials would look like. Now they make this analogy, this is up in the Sierra Nevada, I think I've been backpacking here. So here's Iceberg Lake, Cecile Lake. Yeah, my wife and I may have been along some trails in this area. We certainly saw the minarets. I think we were farther to the east. Anyway, these are topographical lines showing elevation. That's kind of how equipotential surfaces work. The voltage or the potential for each one of those lines is kind of analogous to elevation. And then what the E-field lines do then is, and I think you've seen this in your calculus class, right? You take a gradient of the potential, and that tells you in which direction the function is changing most rapidly. So in this example, the equipotentials are drawn in. See, there's an equipotential at 10,400. Here's an equipotential at 10,800. And then the E-field lines would be perpendicular to all of these lines. So right here, for example, there would be an E-field direction that heads from this high elevation where the minaret peaks are, and the E-field line would direct us back towards Iceberg Lake, which is at a lower elevation. So kind of a similar analogy. All right, here's everything we've done, I want to say, in chapters 21, 22, and 23. What we've done, this is for gravity, sorry about that. What we've done is we've looked at the electric force, and we've gone in and we've looked at the big four. We've looked at electric field, electric force, electric potential, and electric potential energy. Now, let's bring gravity back in here. Turns out gravity works the same way, right? So if we're going to do a summary chart of how the electric force behaves, what are the major players here, what do I have to keep track of? I can always draw gravitational analogies. So in the gravitational case, here's a gravitational field. That's what I'm going to claim we start with, is imagining a gravitational field. Now the gravitational field itself is due to the presence of mass somewhere. Earth's gravitational field, we can determine how much gravitational field we have by knowing the mass of the planet, the gravitational constant, and distances. So here's a gravitational field. There's an object in that gravitational field. It's going to experience a force. There's a gravitational potential associated with the field. There's a gravitational potential energy associated with the force. And so I can work back and forth between force and field. The equation there is F equals mg, and those are vector quantities. They have direction. Or I can work in terms of energy. Instead of working in terms of force, I can work in terms of energy, and that would become our scalars, which are gravitational potential and gravitational potential energy. If we want to be able to work back and forth between the scalar and the vector quantities, we know that the potential differences are determined by following the gravitational field line along some path, and analogous to that is the potential energy following the forces. So in this case, the following the force and the gravitational field, it's the same thing. Gravity is the easier example here because gravity is always attractive. And that means the gravitational field is in a particular direction. The force acting on objects in that field will experience a force in the very same direction. And that says higher potential and lower potential will match up with higher potential energy and lower potential energy. So either approach works, and the vector and scalar equations are just related by the mass of the object. Now what that means is, even before I introduce a mass, I could take that away. Now if I take the mass away, I don't know what the force is and I don't know what the potential energy is, but even without imagining an object, I can still say there's a gravitational field due to the planet Earth. And that means that we can do calculations of field and potential without asking which kind of an object are we going to place in that field. And then here is that calculating the gradient, going in and taking a scalar field. The potential is a scalar field because it has a value, a single value at every location in space. The gravitational field is a vector field. So they're both fields, even though one gets called the field and the other gets called the potential. All right, now the electric force works the very same way, except that when we place the charges in the electric field, there's a possibility that they could be negative. And that says that we've defined the direction of the electric field. If I put a positive charge in there, the force is in the same direction. That's going to work the same way gravity did. But if the charge that we place in there is negative, then the force will be in the opposite direction. So the very same big four, we're going to start with the same big four. It's electric field, electric force, electric potential energy. I got a pair of vector quantities, a pair of scalars. Equations look just the same, except there are Q's instead of M's, and there's an electric field instead of a gravitational field. Everything else is kind of defined with the same symbols. We can define potentials and potential energies. Potentials are defined by looking at a path along the electric field. Potential energies look at the force. Now what happens in this case is I can look at the electric field, and the electric field will guide me away from higher potentials towards lower potentials. But as far as the potential energy, it depends on the sign of the charge. If the charge is positive, then higher potential energy is to the left, lower potential energy is to the right in this particular diagram. But if it's a negative charge, that reverses. So for a negative charge, this side is at the higher potential energy, and the left side would be lower. So same set of formulas that allow us to switch back and forth. So, and you guys will see this in the homework problems, right? Now that we've made it all the way through chapter 23, and we're actually going to take a rest with this stuff. We're going to, for a couple chapters now, we're going to look at electric circuits. So we've kind of done everything we want to do with electric fields and forces and such for now. So this is kind of the summary of what we've done in these 3 chapters. And so they're related through taking these partial derivatives or integrating along paths. All right, we do have a couple more examples in chapter 23, so let's look at this. You guys may remember the electric dipole. Now, we just talked about an electric dipole here. So this will be a useful diagram to keep track of, although I think when I drew the picture here, I reversed the charges. So I put the positive charge on the right, the negative charge on the left. The equal potentials are all going to look the same, but the electric fields, I take that back. The equal potential surfaces look the same, but the signs are reversed. What was positive is now negative and vice versa, and the direction of the electric fields will change. So we're going to keep referring back to this. But let's go in and the idea here is, here's my electric dipole. I have a positive charge and a negative charge that are somehow connected. We said that a couple of good examples of this, we could build mechanical systems that operate this way. Another good example, though, is looking at atoms and molecules. Atoms and molecules, molecules in particular, end up having potentially a polar quality to them. That means that part of the molecule is positive, part of the molecule is negative. electrically they're neutral. Water molecules were, the example that we worked from here. So if I look at a point out in space at some distance, what is the electric potential going to be at that location? So as always, I change my diagrams a bit. So what they called R in the diagram, I actually redefined this. I said the distance between the charges is 2 times A, because it makes some of the math easier to work with. So instead of L, I'm going to use 2 times A. The angle I'm looking at is theta right here, and distance R out to point A. And then I'm going to symmetrically place the positive and negative charges. What that does is I'm now using a polar coordinate system, and the polar coordinate system is centered not on the negative charge, not on the positive charge, but on the midpoint between the 2 charges. That puts me right at the location of the dipole by definition. And so there we go, there's the dipole up there, and the dipole we've been saying is Q times L, but for our purposes it's Q times 2A. And yeah, the P that represents dipole is, I guess it's the P in pole. Anyway, we're working in polar coordinates right now, but we're going to be switching back and forth. So what we could do is say, look, point A has a coordinate location, and I could write that as xy, where x is r cosine theta and y is r sine theta. That's just switching from polar coordinates back into rectangular. Now, if I write down r1 and r2 as the distances from the charges out to point A, I know at point A, both the positive charge and the negative charge will have an effect. Now, when we did this example with the electric field, it was more difficult. And the reason why is the electric field is a vector. And that meant when I looked at the electric fields being produced, I had components. I had to keep track of directions of the electric field, had to keep track of components, and we didn't go very far into this. We looked at a couple simple examples and that was it. But now that we've learned about electric potential, we can say that the potential at point A is equal to the contribution from the positive charge and the contribution from the negative charge. So I'm adding the 2 potentials together. Now, the contribution from the positive charge is going to be kq over r1, where r1 is that distance. And the contribution from the negative charge is going to be kq over r2. Remember, for a dipole, the magnitude of the charge, the positive and the negative charge, they're the same. And so I can just use that one value of q. There's my force constant, little k. The only thing different here, well, 2 things different, I guess. There's a negative sign here, and that means that the charges will offset. Since one charge is positive and one is negative, their potentials will be positive and negative, and there'll be some cancellation. Now, the cancellation won't be perfect for a dipole because in general, R1 and R2 are not the same distance. The only place in this diagram where the potential will perfectly cancel out is along the plane between the 2 charges. Because if I pick a point along that vertical plane that we can see, in that case, R1 and R2 are the very same, and that says the potential is going to be 0 at that location. In fact, this is probably a good time to go back and refer back to our diagram. See that equipotential line right midpoint between the dipole? The potential on that is 0. Because every point along that, if I pick a point right here, equal distance from the positive charge as from the negative charge, contributions will cancel out. All the equipotentials on this side are going to be positive numbers. And as I get closer and closer to this positive charge, those positive numbers are just going to get bigger and bigger. The equipotentials on the other side are all going to be negative. And again, a little negative, more negative, more negative. As I get closer and closer to the negative charge potential will dominate. All right, so let's find a way we can combine this all together. And so what I did is I took those distances, R1 and R2, and I wrote them in Cartesian coordinates. I put them back in rectangular coordinates, x and y. And so the x distance is a little shorter for R1 and a little longer for R2, and that's the only thing that sets them apart. So I wrote this down. Here's the potential from both, 1 over R1 plus 1 over R2, and then I substituted in these two expressions, and I'm calling that my exact formula. So that part of the problem's done. They ask us, to derive a formula for the electric potential at any location surrounding these, and I can write that as the potential as a function of x and y at every location in space is given by that formula. Now, we could have done z, but we don't really need to do z because I can take the picture that I have and I can rotate it around the x-axis. So once we've identified the potential at point A, that applies to a circular path that wraps around that x-axis. So that's it, an exact formula. We didn't get that with the electric field. It was too hard. Now, let's ask ourselves, every time we do a dipole problem, we start by doing these things as an exact formula. And then we go, it's a dipole. What we're really interested in here is what happens in the case where A is really tiny if we imagine the distance between the two charges to be really small compared with the value of R. So we're really looking at distances that are relatively distant, where R is much, much bigger than A. If it's a molecule, A is going to be absolutely tiny, and that means we don't have to get very far away from the molecule until this becomes really useful. Now, if our approximation. Now, if the molecules are in direct contact with each other, like a bunch of water molecules, then we may still have to come back and use the exact formula. It would likely be the case. The approximation doesn't necessarily work. The approximation is going to work better if the molecules are separated. If I had a bunch of water vapor molecules, then we could think in terms of what's the electric potential surrounding that individual water molecule at some distance. Anyway, what we did was, and I hope this is becoming more familiar, this is maybe the third, fourth time that we've looked at these examples. What we can do is, I just carried through, I factored this x minus a and the x plus, I factored out the x minus a. And then I rewrote it, and what I did was I intentionally took the possibly big portions, the x squared plus y squared, and combined those back into R. So at this step, I converted back into polar coordinates. And that becomes useful for us because now what we can say is R is going to be large. R is the big value here. A is the little value. And AR is kind of intermediate. And so this term is going to be the biggest, and then this one quite a bit smaller, and then this one really, really small. And that works as long as either x or y or some combination are large values. And then I factored that big piece out, so it became 1 minus 2a over r cosine theta plus a squared over r squared to the half. So I factored the r out, the big piece. And then I actually did this. Since the formulas for the electric dipole are 1 over r, I thought, why not just go ahead and get an expression for 1 over r1 and 1 over r2. So that's kind of the next step here. I flipped everything over, and I did that by putting a minus 1/2 here. It used to be 1/2, and then here I have the 1 over r. So now we're ready to carry out the approximation. If a is much, much less than r, what I can do is take the stuff inside the parentheses and say that's equal to 1 plus, now I'm going to bring down the minus 1/2 here, and so the 1/2 here cancels. I guess I've got it written out. I got it as 2 steps, so that's good. I brought down the 1/2. The minus signs cancel. I'm left with 1/2 here. And then I looked at the rest of the stuff here, which is 2ar over cosine theta minus a squared over r. Now the idea here is I am going to ignore the a squared term, because if a is really small, a squared is really, really, really small. And so I'm going to ignore that. And my approximation formula for 1 over r1 looks like 1 plus a over r cosine theta. Okay, so that's it. So back here, we are going to, that's what our coordinate system looked like. And now I have an expression for 1 over r1. Well, if I carry out the very same algebra, but this time for r2, I'm going to just flip signs. So the sign is going to change on that smaller term with a minus sign instead of plus. What does that give us? Well, if we go back now, if you remember, the potential is going to come by adding together the potential due to the positive charge and the potential due to the negative charge. And now what I'm doing is I'm taking and replacing these expressions with their approximations. So this path was a little longer, and this path was a little shorter. And, or was it the other way around? Now I've got to go back and double check my approximations. Really? Oh yeah, no, I take it back, because it's 1 over r, it's 1 over r. Never mind. So this 1 over r value is a little bigger, and the 1 over r value here is a little less, gives us something that's a little less. And so this gets the plus sign, this gets the minus. The big parts cancel out. So what's kind of interesting, I guess, in these, using these expansions that you guys have learned in your calculus classes, where you learn these series expressions, is that you can see the big pieces are canceling. What that's equivalent to is that the plus here, okay, now I wrote that as plus, that is a minus sign. I'm going to lose a lot of points on that one. That is clearly a minus sign, get that changed. There's my plus, there's my minus, and the big portions of the potential are going to cancel. And that corresponds to the 1 here canceling the 1 here. But the next terms in that expansion actually end up combining. So even if I had left my a squareds in place, they would have canceled out anyway. And these are the pieces that we would have left. So I combine those into 2a cosine theta over r. And then I recognized that q times 2 times a, that's the length between the two charges. So 2a is right there, which could also be included on that diagram. And so this is it. This is the approximate formula for the potential around a dipole, where r is the distance from the center of the dipole, and theta tells us at what angle we're looking relative to the axis of the dipole. And now I've switched back into polar coordinates again. So I've gone from polar to rectangular to polar to rectangular back to polar, and this is a handy way to represent our approximate formula for anywhere in space. As long as we don't get too close to the dipole, this is going to be a useful formula for us. Now it makes some predictions here. If I put in some values of, let's just put in a value of r and give us a spherical surface. Ooh, does that look spherical? Okay, I'm imagining that's a spherical surface. What that tells us is when theta is equal to 0, I'm going to have an electric potential that's positive. And the electric potential will be positive at that location. It will have a value of Kp over r squared. Perfect. Now, as I start walking around, let's do a walk around of the dipole. What happens to I get the plane at the middle? Well, that would be 90 degrees. That would say the potential is 0. And that's what we talked about, if you remember, back on this diagram. So over here, the potential, oh, yeah, these are switched. So over here, by the positive side, the potential is positive. By the time I get to 90 degrees here, the potential has dropped to 0. So it's all being taken care of with that cosine function. When I cross from 90 degrees and beyond, the cosine goes negative, and now it's keeping track of this region where all the potentials are negative. And the most negative locations are going to be over here at 180 degrees. And so I'm going to have minus kp over r squared. Here I'm going to have another 0, so yeah, it seems like it works. Now remember, the potential is a scalar, and that means that at every location in space, there is a scalar number that tells us what the electric potential is at that location. Does not involve directional information. It's just how far am I from the positive charge, how far am I from the negative charge, combine those two effects together and see what we're left with. All right. Now, once we've come up with this formula, remember now that we have formulas that will tell us, if I start with a potential, how could I go in and determine the electric field components? So at point A, I am going to have some electric field components. I could have an electric field component in the x direction. I could also have an electric field component in the y direction. I'm actually expecting both. How would we get formulas for those for those electric fields? And what we can do is come back and use our partial derivatives. So I've got this expression for the potential that we came up with. Once again, I'm converting everything back into rectangular coordinates because I want to be able to take partial derivatives. If I'm going to take partial derivatives with respect to x, partial derivatives with respect to y, I need to have my potential written in terms of x's and y's. That's how it works. So I put everything back into x and y, and then I took that partial derivative with respect to x. Now I'm not leaving out the y component, it's on the next page. But I started with the x direction, and I saw this as an opportunity to go in and practice the quotient rule, that's the best rule in differential calculus, right? Bottom times derivative of the top, minus the top times the derivative of the bottom, over the bottom squared. I love that rule. So that's what I did. Bottom times the derivative of the top, top times the derivative of the bottom, over the bottom squared. And what that gave me, now everything over here that is x squared plus y squared goes back and becomes r again. So that denominator becomes r to the 6th. Now in the numerator, there's a minus sign here. I carried the minus sign through, so those numerator terms got reversed. Just to let you know what's going on here. So this one, which looks like r to the 3rd, actually has the minus sign now. And this other one, which has r, and then the 2's cancel, I got a 3. Wherever I have x squareds are related to cosine factors. So the x squares become r cosine theta, and those show up as cosine theta here. And then when I get finished here, I brought all the factors of r out. There were 3 factors here and 3 factors here. And that's what I ended up with for my x component of the electric field in formula, in the formula here. So there it is. That looks pretty good. So 3 cosine theta minus 1 kp over r to the 3rd. I switched back into polar coordinates. All right, excellent. We can think about what that looks like, but let's get the y component first. So the y component calculation is completely analogous to the x component calculation. I'm going to take the potential and take a derivative with respect, partial derivative with respect to y. I get to use the quotient rule again. Yes, I really like the quotient rule. And this time when I did the quotient rule, I just ended up with one factor. So I'm taking derivatives with respect to y, and if I go back, I guess I gotta go back one here. This expression right here has y dependence in the denominator, but it doesn't have any y dependence on top. So I did the quotient rule anyway. And so when I took derivatives on top, it gave me nothing. So that factor canceled out. See, I even used the quotient rule when maybe I shouldn't have. I look for opportunities to use the quotient rule. So I did this, the minus signs canceled out, I converted back into polar coordinates, and there they are in polar. So there it is, there's my y component formula. So using this formula for the y component, and the one on the previous page for the x component, see what those look like. They got both. Let's look at the common features here. It says the dipole drops off by 1 over r to the third power. So a point charge by itself would have an electric field dropping off like 1 over r squared. Well, dipoles drop off at a faster rate because the two charges tend to cancel each other's E field. Not completely, but partially. And so the drop-off is more rapid due to a dipole than it would be due to an individual point charge. That's to be expected. So I went through and I drew the diagram here, and so here's what I came up with. Because the E field Y component formula has this cosine and sine factors in them, they went zero. They went to zero here, and they went to zero at 90 degrees, and 180, and 270, and back to zero, or 360. At all those four locations, there is no Y component. Now, at 0 and 180, my X formula gave me a positive number. Let's go back and take a quick look at that. This is an even function for the cosines. The cosine itself is an even function, and we've squared it. So it doesn't matter here. We're going to get a symmetry here. Whether it's 0 or 180, that's going to give us the same result. Okay, now what does happen at 90 degrees is that term drops out and it goes negative. So you can see that over most of the angles, this will be in the positive direction. But as we approach 90 or as we approach 270, these terms will tend to, well, they're going to be much reduced. And as a result, we're going to end up with E field components in the negative direction. So the E field is directed negatively here and negatively here. And if you flip back to that diagram of a dipole, that's what we predicted. So these E fields right here are directed right across those equipotentials. Now, since I didn't get any Y components here, I moved on to 45 degrees and 135 degrees at pi over 4 and 1/4 pi and 3/4 pi. And in those cases, I got X components, which were still pointing in the positive directions at those two locations. And then here I got a vertical component. So, and if you follow this on that diagram back where we drew the equipotential surface, it's kind of a teardrop shape here that we're expecting that the electric field would follow. And that's what these E field components are telling me. At 1/4 pi, the components are positive vertically and positive in the X direction. And when we get back to this 3/4 pi location, what we have is still the X component forward, but now the Y component is what we're calling the negative direction. And then I was going, you can see how large these are. This is 1/2 kp over r cubed. Everything is a factor of, has a factor of kp over r cubed in it. So it's useful for going in. One last look at that dipole. That's what it's showing us. So what's happening here is, again, I guess we got to imagine this is positive and this is negative, so all the arrows reverse. But we're following one of these teardrop lines like this. Okay. So that's what it looks like. And actually, let me draw that one more time. The teardrop is actually centered at the point between the charges. Remember, the formula we're working with doesn't work if we get really close to the charges. It works when we're far, far away from where the charges are located. All right, just think, that's a molecule of some sort, hydrogen fluoride. All right, so that's a good problem to go through and take a look at. It's a good example. It's doable. First of all, it's doable. It's in the category of something that you actually can carry out all the calculations, and it shows us a lot of how the potential and the electric field components are related. So it allows us to kind of experience a fairly high-level example with interesting stuff going on, but still doable. It should be no more difficult than some of the homework problems that you see in your calculus classes. All right, this slide, it's just a reminder. It's just saying that, remember, we can calculate an E field. If I know the potential everywhere, I can calculate an E field. All right, and we can go in and get all of the components that we needed here. All right, a couple of items that I want to include here that didn't get as full of a treatment. It's in the textbook, it's in previous slides. I just wanted to bring a couple things back. First thing I wanted to ask about is, okay, what happens if I just have 2 point charges? And we can go back and use the potential energy formula. U is equal to little k, electric force constant, Q1, Q2 over R. And that positive, positive, or negative, negative contributions, where there's repulsive forces, that potential energy will be positive. So if I take 2 positive charges, I actually have to do work on them. I have to push to hold them together, but once I've done that work, I've now stored up potential energy. If I let go, I get that potential energy back as kinetic. Now in the case where positive and negative combinations occur, one is positive, one is negative, the potential energies here are going to be negative, and that indicates an attractive force. Now in the attractive force case, I actually have to put the brakes on, right? Because the 2 charges are trying to attract each other. And so I am holding these things so that they don't slam into each other. Now once they're close together, there's an energy debt, which means that in order to bring them apart, I'm going to have to pull to bring them apart. And that's why we use negative potential energies here and positive here. What happens if we add a 3rd charge, or a 4th, or a 5th, or a 6th, or a 7th? If I bring more charges in, what I can do is look at all of the pairwise interactions. Now, pairwise means I look at the potential energy between charges 1 and 2, I look at the potential energy between charges 2 and 3, and I look at the potential energy between charges 3 and 1, and I add them all together. If I were to step by step combine these charges, I imagine starting with the charges separated out to infinity. So I'm keeping these 3 charges way far away from each other. And then I bring the first charge in. Well, bringing the first charge in by itself doesn't change anything because the other 2 charges are still out at infinity. But when I bring the second charge in, I create this interaction. And so this interaction right here, there's now going to be a potential energy. What happens when I bring the 3rd charge in? Well, I got these 2 charges here, and I bring in a 3rd charge. That 3rd charge is going to interact with charge 1 and charge 2. So bringing in the 3rd charge will introduce 2 additional terms. What happens when I bring a 4th charge in? Exactly. So when I bring a 4th charge in, with 3 charges already present, I'm going to add 3 additional terms because now charge 4 interacts with 1, 2, and 3. Now, it doesn't matter which order I bring the charges together. I could start with charge 3, and then I could bring in charge 4, and then charge 2. It doesn't matter which order I bring them in. By the time I have assembled these point charges, I will have a term in my potential energy formula representing each possible pairwise interaction. Each interaction between a pair of charges is represented with one of those terms, and I have to add them all together. I'm not supposed to say, and then I just have to add them all together, but hey, these are scalar quantities. This is much faster than doing vector addition with forces. Here, I can just add these numbers together. Some could be positive, some could be negative. Okay. Now, another item that we want to say is important in this chapter, we don't want to overlook this, is a new unit of energy. The potential energy of a charge is given by Q times V. It's kind of the same thing we've said before. Let's see, here it is. Here's the new unit. So what we do is we define an EV. Now, they used to be called electron volts, and I guess they still get called electron volts, but when I was in physics research and particle physics, we just always call these EV. It's kind of like no one says electron volts. EV is a really handy unit because if I have an electron or a proton, they each have the same amount of charge. And so if I have an electron moving through a potential of 1 volt, I can say that that potential energy represents 1 EV, which would be the charge of the electron times a volt, which gives me 1.6 10 to the minus 19 joules. Let's look at an example of using this unit. Now, instead of an individual electron, let's imagine a helium nucleus. So, in fact, this is a helium-4 nucleus. It's got 2 protons and 2 neutrons. And so the charge is 2 times E. Let's say that we put that in a region where we have a potential, an electric potential of 5,000 volts. How much potential energy difference will there be between points A and B if the plates are charged to a potential of 5,000 volts, and these are helium nuclei? Well, what I can do is say the potential energy is Q times V. Now, since they're helium nuclei, it's 2 times E times the voltage. The potential energy then, that between points A and B, will be 10,000 EV. So fundamental charge times volts. Now that says that when this leaves the region between the 2 plates, it's going to have a kinetic energy of 10,000 EV. Now, if I'm going to do some additional calculations of how fast this is traveling, then I probably want to switch over and use joules. In fact, I need to. And so I'm going to convert those EV into joules. So when we're working with electrons or protons or helium nuclei or some simple atomic or molecular system, it's often easier to work in terms of fundamental charges. And so, you should be ready to do calculations both in EV and in joules for these potential energies. Now, if I wanted to find out how fast it's going, I could say the kinetic energy, I can set that equal to 1/2 mv squared, solve for V. Here is my energy in joules, which it's going to need to be because I'm going to put a mass in kilograms. So a helium-4 nucleus has a mass that's 4 atomic mass units, and then I did a conversion into kilograms, and it turns out at 5,000 volts, these helium nuclei are really going fast. This is 694,000 meters per second after traveling through an electric potential of 5,000 volts. So directly I can go from volts and do a series of calculations and get speed. The only thing I needed additionally along the way was the mass and the charge. So if I know the mass of the particle and the charge of the particle, I can do that calculation. I don't have to solve for accelerations. I don't have to solve for forces. I don't have to solve for electric fields. I can do this completely in terms of energy, energy conservation, and then once I get the kinetic energies, using the kinetic energy to do a velocity calculation. Now here's another example that the textbook has produced. They say, well, what about the hydrogen atom? And so let's take a look at what they're saying here. They're saying in a hydrogen atom, I have a proton, I have an electron. Now, I'm going to drive home this point of when we're looking at atoms and molecules, it's very, really important you understand how the charge is distributed. So, first of all, the nuclei, in this case, it's a hydrogen atom, so the nucleus is just a proton. But the nucleus can be thought of as a point charge. We've been talking about point charges in chapter 21 and chapter 22 and chapter 23. Well, here's a good example of a point charge in nature. Those are the nuclei. The nuclei are absolutely tiny compared with the size of an atom or a molecule. And so the point charge approximations work really well. Now the electrons, as you guys know from your chemistry classes, or your physical science classes in high school or whatever, the electrons are spread out. First thing you want to remind yourself is the electrons are not orbiting the nucleus. The electrons are going to be represented by a probability distribution of charge. So in the hydrogen atom, there's just the one electron, but that electron is going to have to be thought of as a distribution of charge, maybe a spherical distribution. So we've looked at that also, right? What are the properties of a point charge, like the nucleus here, the proton, and what are the properties of a distributed spherical distribution of charge? So you got to start thinking of the electrons that way if you're not already. I hope your chemistry classes, if you're taking chemistry classes, and if you've taken them, have really emphasized that. So what they're going to do here is they're going to say, okay, the proton, let's think of the proton as being a point charge, and it's going to generate an electric potential, and that potential will have different values depending on R. Now, strictly speaking, the electron has a variable R, distance from the proton. It can't be thought of as just having one fixed value of R. It has to be thought of as a combination of all the possible locations that the electron could possibly be. Now, the way they got around it in this problem is they said, let's just use an average. Let's use an average distance. So a good average distance, and we'll see why this was chosen in Physics 4C, they picked what's called the Bohr radius. They said, okay, kind of on average, the electron is 53 picometers from the nucleus. So I plug that number in, and it says that the electric potential due to the proton at this average distance of the electron is 27.2 volts. And that says that if I now add in the charge of the electron, its potential energy is minus 27.2 eV. And again, we're down at the level of atoms and molecules. We tend to use eV as a unit. So this is the potential energy of interaction between a proton and an electron. So in hydrogen. And so this is a number that we'll find out in Physics 4C. We're going to get it using equations from quantum mechanics. But it does turn out that this average distance that they've chosen correctly represents, correctly gives us the potential energy associated with this interaction. So rather than carrying out a complicated integration, we just averaged and came up with that. That is the potential energy for this hydrogen atom. Now, it turns out the hydrogen atom is more complicated. This is what's called the Bohr model of hydrogen, so I'm not going to go into details of all the, I'm not going into the details of this, but kind of when quantum mechanics was first becoming established, Niels Bohr, a Danish physicist, suggested that one way to carry out the calculation would be to imagine the electron following a circular orbit. That's not right. Okay, so let's be clear about this. The Bohr model of the atom is wrong. Okay, I mean, my grandma was Danish, but I'm still going to say the Bohr model of the atom was incorrect. But it was a useful conceptual stepping stone. So don't get stuck there. You got to, at some point, make the full transition into quantum mechanics. Anyway, in that model, well, the kinetic energy of the electron is viewed as 1/2 mv squared, which it works. The potential energy is what we just calculated. It turns out that when you do a full-blown analysis, you find out that not only is there potential energy between the electron and the proton, the electron also has kinetic energy. So the kinetic energy of the electron becomes 13.6. This is in the Bohr model, which is wrong. It also is a number we get from quantum mechanics. So it's kind of this coincidence that Niels Bohr came up with the correct energy calculations, the correct energy formulas, by making a series of incorrect assumptions about how the hydrogen atom works. Anyway, that's a good skill to have, right? Make a series of incorrect assumptions, but get the right answer. So it turns out that the binding energy for an electron, it's not minus 27.2 eV, it's only minus 13.6, because the electron already has 13.6 eV of kinetic energy. The electron does not have 0 kinetic energy. It has 13.6 eV of kinetic energy already. And that is the lowest possible energy state. It's the lowest possible quantum state within the hydrogen atom. Just so you guys are, sometimes with atoms and molecules, it's presented as if it's all about the potential energy, but the energy involves both kinetic and potential contributions. Both of those have to be considered. All right, this is the rest of the Bohr derivation, but I don't think I'm going to go into it. They may have, I'm trying to remember if this is a follow-up to their question. Anyway, no, I don't think so. I think I filled in stuff I didn't need to. All right, so again, to kind of drive home that point, this is a space-filling model of the H2 molecule. Now we're looking at molecules. Here's a hydrogen nucleus. The electrons are spread out. I just put that there so that, so don't think this way. So I found a bunch of diagrams also online. Here is an H2 molecule with a stick. Now I know if you're a molecular biology major or whatever, you know that the molecules are always getting represented this way. But we don't want to conceptually think about that. We always want to think of them as space filling. So this is one of my favorite molecules, is glucose, sugar molecule. And so, there's carbon atoms in here, and there's oxygen and hydrogens. And at the center of each one of those little spheres, those merged set of spheres, is a nucleus, which can be treated as a point charge. But this space-filling stuff is the electron distributions. So the electron distributions, you can see, once you include the electrons, how molecules take up space. It's very common to say, atoms and molecules are mostly empty space. I don't think so. Try sending something through that empty space, because the electrons are spread out. The electrons are everywhere, and you're going to run into electrons if you try and push something through this. Okay, and so I added this as an example. Here is the hydrogen molecule. So this is kind of in reference to what I was looking at before. What happens when we look at molecular hydrogen? Well, point charge, there's a hydrogen nucleus. Its chemical formula is H2. And then here is a set of electrons in some kind of a spatial probability distribution. Now, what I did in this problem is, I probably shouldn't have calculated it this way. I looked up the bond length of H2. It turns out that the two nuclei are separated by 74 picometers, in an H2 molecule. And then I said, okay, let's try out this potential energy formula, the one we saw a few slides back. Let's put in 2 protons and 2 electrons. How many interactions do we have? And we've got 2 repulsions. The 2 nuclei are repelling each other. The 2 electrons are repelling each other. And each proton-electron pair, there's an attraction taking place. So if I think of this in terms of potential energy, I'm going to have 2 attractive terms, 2 repulsive terms with a plus sign, and 4 attractive terms with a negative sign. Now the distances aren't the same. So for the repulsive terms, I use the 74 picometers. That clearly is the distance between the protons. Now, the electrons are all over the place, so that makes that a more difficult calculation. What I did was I just said, okay, let me just do a very, very rough approximation. Let's treat the electrons also as point charges, also separated by this bond length. Let's imagine that they form a square. And so I got 2 protons and 2 electrons forming a square, and the idea is that going to be something where the potential energy will be overall negative, or is it going to be positive? If I place 2 positive charges and 2 negative charges at the edges of a square, is the overall potential energy going to tend to draw those together, or is it going to push them apart? And I could carry out the calculation. So what I did was took 2 repulsive terms, 4 attractive terms, and I added them together. And I ended up with, now at some point I did do EV. So I calculated these as joules, which is done right here. Oh, that's what I did, right. So I did the KE squared part. So I wrote KE squared. It turns out KE squared by itself, I wrote that in standard units. And then what I did was I did a couple conversions. I converted, and this needs a square on it, right? No, I don't need a square. Okay, just want to make sure we've got all the units right here. So I converted one of the distance units, and I converted one of the joules, but not both. So I had a joules here. Yes. Okay. So I needed a conversion into nanometers, a conversion into EV. Take a look at the units and see if they make sense. Turns out that KE squared can be represented as 1.44 EV times nanometers. So that sets us up so that when we're carrying out these sorts of calculations, these sorts of calculations are always going to have KE squared in them. So I calculated the KE squareds up front in some handy units, and then what that enabled me to do was the R's now could be put in as nanometers, and the nanometers would cancel. So I'm going to claim that once you work with this shortcut a few times, you'll see that it's a shortcut. It's a shortcut that gets used to calculate kinetic and potential energies inside these molecules. Now, the overall potential energy of that charge system, which was a rough approximation for hydrogen to an H2 molecule, I've got negative 71.9 eV, whereas in just a hydrogen atom, I had minus 27.2. So the question then becomes, is the hydrogen molecule stable? And the potential energy alone suggests stability, but remember, the electrons will have kinetic energies also. Turns out the electron kinetic energies are like before, maybe 10 or 15 eV, and so that's enough potential energy to offset it. And I guess you would have to look up the, what does it take to completely disassemble an H2 molecule, but we could go in and determine how much kinetic energy those electrons have. Just as an aside, the protons also have kinetic energies, but not nearly as much. So the protons are able to shift back and forth a little bit. In fact, that's what we called vibrational energy, vibrational kinetic energy back in the thermodynamics chapters. So just getting back to thermodynamics, the protons can have a little vibrational energy back and forth. So a little bit of kinetic energy in the protons, more kinetic energy in the electrons, and then that is offset by this binding energy. All right, so the overall effect is that the molecule stays together. Overall, the energy is negative, and that means that there's a certain amount of chemical potential energy associated with that molecule. All right, here's that glucose molecule again. Sweet, right? Not as sweet as fructose, but... All right, so here is another example. And I'm going to call this my example of chemical potential energy, because when people list all the different types of energy, they always talk about chemical potential energy. Is that something related to electric potential energy, or is it something entirely different? And so I picked out one of my favorite chemical reactions. So here's glucose, and it's reacting with oxygen. I'm breathing, and as a result, the glucose is broken down, and the oxygen, and all these chemical bonds rearrange, and I end up with 6 carbon dioxides and 6 waters. Now I know in a biological system, it happens in a bunch of steps, right? You've got glycolysis, and you've got Krebs cycle, and all kinds of stuff, oxidative phosphorylation going on. But if we just think of that as an overall chemical reaction and ask how much chemical potential energy is there in this reaction, what we can do is say, okay, the glucose molecule itself, all the electrons in there have some amounts of kinetic energy. There's a potential energy of all the attraction between the electrons and the nuclei. The oxygen molecules also kinetic and potential energies. CO2 molecules, H2 molecules, they all have combination of kinetic energies and potential energies. Now, some of the energy of the molecules, when we're placing them in a, here's a container containing some of these molecules, they're additionally going to have translational kinetic energies as well as these rotation and vibration energies to them. So what happens in this is energy is conserved. But what happens is the kinetic energy of translation and rotation and such of the products is going to be greater. So the kinetic energies of translation and rotation and vibration in the products will be larger than the kinetic energies of what went in. That's like thermal energy goes up, right? If I've got more translation and more vibration and rotation, the temperature went up. Well, this is an exothermic reaction. Now, the energy itself is conserved, but what happens is CO2 and H2O have lower potential energies. So CO2 and H2O are well-known, very, very stable molecules with really low potential energies. And so since the potential energies for C and D got deeper, they're more negative, that means that the kinetic energies of those molecules are more positive. So if I look at all the kinetic energies and potential energies of these molecules, overall the potential energy, the electric forces, have an overall lower potential energy, and that means the kinetic energy of those molecules will be higher, and that's the release of chemical potential energy into kinetic energy. The molecules are moving faster, things are at a higher temperature. All right, there's a couple of things here at the end talking about forming electron beams and TV sets from 20 or 30 years ago, which I'm not going to worry about. I think that's it. I think we are through the chapter. So I think there's a good place to stop. So I'm going to stop with the glucose molecule. Or maybe a representation of chemical potential energy converting into kinetic energy of the molecules, the release of chemical potential energy in an exothermic reaction.